Hi everyone, how is your break? Welcome to our first online class. So last time we talked about session 4.6, the Poisson approximation to the binomial distribution. So what is the Poisson distribution? It has PMF, small f, k, lambda. So here lambda is the parameter, okay? So you can see here that is the PMF, that is the probability x equals to k, and this is the formula, e to the minus lambda times lambda to the k over k factorial. Okay, so for Poisson distribution, we actually use CDF to compute. So CDF is the capital F, k, lambda. And do you remember what is CDF? CDF is probability x less than equal to k. Okay, and the CDF values is in table 2. Okay, so do you remember what are the discrete distribution we learned? We learned binomial distribution, and for binomial distribution, it's better to use CDF to calculate. So CDF is in table 1. And then we talk about the geometric distribution. So for geometric distribution, it's better to use PMF to calculate, and we have the formula for it. And then we learn about hypergeometric distribution. So we also use PMF to calculate. And now we have the Poisson distribution. So for Poisson distribution, we use CDF to calculate. So actually, you can just look at your table. Table 1 is the CDF for binomial distribution up to n equals to 20. And then table 2 is the Poisson distribution. So if you can see the distribution in the table, then for those kind of distribution, we can use CDF to compute. Otherwise, we use PMF to compute. Okay, and we know that for Poisson distribution, the mean and variance are both lambda. Okay. All right, and then we have the famous theorem, law of rare events. So when n, that means when n is large and p is small, we can use Poisson distribution to approximate binomial distribution. Okay? And last time we did example 1, right? So part A, we use binomial distribution. But here, because n is 100, we cannot use CDF values in table 1 to calculate, because table 1 only covers n up to 20. But however, we can use the PMF for binomial distribution to calculate. So this is the formula. Remember, we have 100 trials, we have 2 success. So probability of success is 0.05. That's why we have 2 success, and how many failures? 98 failures. So this is the formula of the PMF of binomial distribution. Okay, if we want to use Poisson distribution to approximate it, so here we have to figure out lambda. So for binomial distribution, the parameters are n and p. For Poisson distribution, the parameter is lambda, and lambda equals to n times p. So we first figure out lambda, and then there are 2 ways to use Poisson to calculate Poisson distribution. We can use the PMF, which is this formula, or we can use CDF, which is table 2, and I suggest you to use CDF to calculate. Okay? So let's continue on example 2. All right. So in a given city, 6% of all drivers get at least 1 parking ticket per year. Use Poisson approximation to binomial distribution to determine the probabilities that among 80 drivers randomly chosen in the city, 4 will get at least 1 parking ticket in a given year. At least 3 will get at least 1 parking ticket in a given year. Anywhere from 3 to 6 inclusive will get at least 1 parking ticket in any given year. Okay, so what is part A? 4 will get at least 1. What is at least 1? So that actually is the success, right? Success is get at least 1 parking ticket in a given year. So that is the success. Okay, so part A is asking px equals to 4. Okay, and we know this is a binomial distribution because 60% of all drivers success, so probability of success is 0.06. And we pick how many drivers? Yes, 80. So that's why this is binomial distribution. But because n is 80, 80 is quite large. It's bigger than 20. So we cannot use the table 1, the CDF for binomial distribution to calculate. That's why we use the Poisson distribution to approximate it. Okay. In order to use Poisson distribution, we have to compute lambda. So lambda is n times p. N is 80. P is 0.06. And do you know what is that? What that is? Well, that is 4.8. Right? So that is 4.8. You can see this problem, n is large and p is small. That's why we can use Poisson distribution to approximate the binomial distribution. So later on in chapter 5, we will learn when n is large, but p is not small, like close to 0.5. We actually use the normal distribution to approximate the binomial distribution. So we will talk about more in chapter 5. Okay? Alright, so let's continue. So x equals to 4. Well, that is the PMF of 4, where my lambda is 4.8. Right? So we know there are 2 ways to compute it. Is either use the PMF way or use the CDF way. So here I'm going to show you both. Again, it's just like a review. Okay? So, what is the formula for the PMF? Well, that is e to the minus lambda. Lambda is 4.8. And then lambda, 4.8 to the k. K is 4. All over k factorial. So that is 4 factorial. Okay, so plug this in your calculator. What do you get? So let me plug it in my calculator. E to the negative 4.8 times 4.8 to the 4 divided by 4 factorial. So that is 4 times 3 times 2, which is 4 times 6, and that's 24. Okay, so my answer is 0.18202. So that's the same as 20 if we need 4 decimal places. Okay, so that is how to use PMF to calculate. How about we use the CDF to calculate? Well, when we use CDF, that is table 2. Okay, so small f indicates PMF, capital F indicates CDF. So what is exactly 4? Exactly 4 is what? Less than equal to 4, subtract less than equal to 3. So that's why 4, parameter is 4.8, minus less than equal to 3, parameter 4.8. Okay, so what is that? Well, let's find those numbers. So let's get our table. So this is table 2, the CDF values for Poisson distribution. Lambda, our lambda is 4.8. So next page. So 4.8 is right here. And let's see, we first find f of 4.8. This number 0.476. 0.476. And then next, we want to look at lambda is 4.8 and k is 3, which is 0.294. Are you able to find those numbers? 0.294. Okay, so we use 0.476 minus 0.294. What do we get? Plot this in your calculator and we get 0.182. You see? They are the same. Yay! Okay. So that is part A. Okay. So part B. Let's see part B. So the good thing about watching the videos is you can control your speed. You can pause in each step and think. So I strongly recommend you to pause here and then try to work on part B. And then we can check our answer together. Okay, pause. All right, are you done? Okay, let's continue. At least 3 will get at least 1 parking ticket in a given year. So at least 3, what does at least 3 mean? Greater, equal, or less than equal? Yes, greater than equal. Wow. How do we compute greater than equal? Remember CDF, we use less than equal. So greater than equal, we don't want to see greater than equal, so we consider the complement. What is the complement of greater than equal? Yes, less than, but we don't want less than, we want less than equal. So less than 3 is the same as less than equal to, yes, 2. Okay, so that is 1 minus the CDF of k is 2, lambda is 4.8. Alright, so let's see what is that. So come back to our table. Lambda is 4.8, and then, oops. So you can see here, this guy, right? 0.143. Okay, so we continue. 0.143. So 1 minus 0.143 is, what do you get? 0.857. Do you have the same answer? Okay, so that is part B. How about part C? Anywhere from 3 to 6 inclusive. So 3 to 6 inclusive. So include the endpoint. So what is that? Well, 3 included, 6 included. So you want to have less than equal to 6? Subtract. Do you want to subtract 3? No, we want to subtract the 2, so the 3 is left. So this is F, 6, 4.8, minus 2, 4.8. Okay, what are those numbers? Let's go back to our table. So 4.8 here, 6, that is 0.791 minus 2, that is 0.143. 791,143. 791,143. Okay, plot this in your calculator. What do you get? I get 0.648. Do you have the same answer? So that is how we use the CDF values for Poisson distribution to compute the example. Okay? So if you have any questions, please print screen and then ask me either through emails or through online office hours. Okay? So that is session 4.6. We introduced the Poisson distribution. Next, 4.7, we're going to talk about Poisson process. So the goal of this session is to find the probability of X successes during a time interval of length t. So this is abstract definition, right? So it's very good to think about an example. So a time interval of length t. So t could be 1 day, or it could be 2 minutes. It could be 5 seconds. Okay? So any time interval t, right? And then we're gonna divide the interval into n equal parts of length change of t. So let's draw a picture. We have, this is t. Okay, so we want to divide into n equal parts. Okay, so each part is change of t. Then what is change of t? Well, that's t over n, right? It's the time interval divided by n. And then we also know that t equals to n times change of t. Okay? Next, we let alpha be the average number of success per unit of time. What does that mean? Maybe, for example, like alpha could be 5 successes per minute, something like that. Okay, so is average number of success per unit of time. Okay, so for example, 5 successes per minute. Okay, now assume 3 parts. Part 1, probability of a success in change of t is alpha times change of t. Or what is that? What is change of t? Let's say if change of t, it could be 1 second. Okay, then let's say our time interval, like the t, it could be maybe 10 minutes, and change of t is like 1 second. And then what is the probability of success in change of t, which is like a probability of a success in 1 second? Well, that is the 5 success per minute times 1 second. But what is 1 second? 1 second is actually 1/60 of a minute, right? And then you like cancel out the minutes, you get 5/60 is like 1/12 success. Okay, so that is the probability of a success in change of time. Alright. Okay, second, the probability of more than one success during the change of t is negligible. Why is that? Think about it. If n is getting bigger, then change of t is very, very small, right? So that's why, because the time is very small, so it's okay to assume there could be only one success during that time interval. Okay, so now you can think about, we have construct this, and then now it becomes like a binomial distribution, because each change of t, we can think about each change of t is like a trial. And here we have n trials, and we're looking for maybe k success in n trials. Well, that is exactly the binomial distribution. And because when change of t getting smaller, we can assume that there could be only at most one success during the time change of t. And the probability of success does not depend on what happened prior to that time. So actually, this guy means all the trials are independent. Okay, then it satisfies the criterion of binomial distribution. Alright, so probability of X success in time interval t. Well, we know it looks like a binomial distribution with a number of trials n, and the probability of success is p, and number of trials equals t over change of t. And the probability of success is alpha times change of t. When n goes to infinity, from the previous session, we have the law of large events. It tells us that when n is large and when p is small, then we know the Poisson, we can use Poisson distribution to approximate the binomial distribution. So use Poisson to approximate binomial distribution with the lambda equals to n times p. And then what's n? N is t over change of t. What is p? Well, p is alpha times change of t, right? And then now change of t cancel, we just get alpha times t. Okay, so now you just need to remember lambda, okay, is alpha times t. So this is the formula for Poisson process. Okay, now let's see how to work on the examples. So let's look at example 1. A bank receives on the average 6 bad checks per day. So what is this number? Well, when you see the keywords average, then you know that is alpha. So alpha is the average number of success per unit of time. So in this case, alpha is 6 bad checks per day. And you see here, bad checks is actually success. So success is not necessarily good things. It could be bad things. It's just something we want to measure and calculate. Okay, so per day. And you can see the units here is day. So be careful because like sometimes our T unit is like here minutes and your change of time is second. You have to change the second into minutes in order to calculate, to make the units consistent. Okay. All right. So part A. 4 bad checks on any given day. On any given day, that means what's the time? Any given day, that is 1 day. Right? So alpha is 6 per day. The unit is day. Okay? Oops. All right. And then, okay, we can use the Poisson distribution to calculate because then lambda is alpha times t. Alpha is 6. T is 1. Oh, so lambda is 6, right? So the probability x equals to 4. 4 bad checks on any given day. Well, that is, well, you can use PMF or CDF to calculate, but it's easier to use CDF to calculate because you just find 2 numbers from the table 2 and then you subtract. So it's much easier in this case. So what is 4? So 4 is less than equal to 4, subtract less than equal to 3. So F4, lambda is 6 minus 3. Lambda is 6. What is that? Well, let's look at our table. So let's see. Lambda is 6. So we're here. And then we have 4, right? 4 is 0.285 minus 0.151. Okay? So 0.285 minus 0.151. So plug this in your calculator. What do you get? So the answer is 0.134. Okay, so that's part A. Oops. Part B. So part B. Alright, so you can pause here and try to work on part B, okay? After you're done, you can continue to play the video and check our answers. Okay, are you done? Yes? Okay. So 10 bad checks on any 2 consecutive days. So T is actually 2 days. Alright, then what is lambda? Well, lambda is alpha times t. Alpha is 6. t is 2. So actually now lambda here is 12. You can see for Poisson process in different parts of the problem, depending on your time interval t, the lambda might change. Okay, so you have to be very careful. Your lambdas for Poisson process not necessarily stay the same for different parts of the problem. It might change. Okay, so here we have 10 batch x. So x equals to 10. So what is that? What is 10? That is less than equal to 10. Subtract less than equal to 9. So 10 lambda is 12 minus 9. Lambda is 12. Let's find our table. Okay. All right. So remember, for your table, you're going to use your table in your homework and all the exams. Try not to write anything on your table. But right now, because I'm showing you, so I draw it. I draw it here. Oh, so you can see lambda is 12. But we are looking for what? The k values is 10 and 9. Oh, let's look at our table. Wow, we only see the 9. We don't see the 10. What happened? Well, don't worry. It's actually next page. So, next page. And actually next 2 page. So you can see here, this is lambda equals to 12. And the 10 is actually right here. So it's 0.347. Okay. And let me erase that. Let's come back. Okay, let's come back here. All right. So we get 0.242. So 0.242. So plug this in your calculator. What do you get? You get 0.105. Do you have the same answer? Good. See, actually it's very easy. We first figure out what's lambda, and the keyword is average. Okay, and then we figure out the t, and then lambda is alpha times t, and then we use the CDF values in table 2 to calculate. Okay, so let's look at example 2. So could you please pause here and then we'll try to work on this problem, and then we continue and check our work together. Okay, all right, are you ready? Let's go. So in the production of tin plates, 0.2 imperfection is spotted per minute per on average. You see the keyword on average, so that's alpha. Part A, find one imperfection in 3 minutes. Oh, so the t is 3 minutes. Okay, and so what is lambda? Alpha times t. So 0.2 times 3 is 0.6. And we are looking for one imperfection in 3 minutes. Okay, so that is... Okay, so what is px equals to 1? Is actually f x less than equal to 1. What is the Poisson distribution start? Does it start with 1 or start with 0? It starts with 0. So actually, if you want to find the x values at 1, you actually need to subtract. Okay, use f1.6 minus f0.6. Yeah, this is a common mistake because Poisson distribution does not start with 1, it starts with 0. Okay, let's find our table. So our table, let me erase this. Okay. Oops. So, all right. So 0.6 is right here. Okay, we use the 1 minus the 0. So 0.878 minus 0.549. 878 549. Right. Okay. So what do we get? Plot this in your calculator and we get 0.329. Do you have the same answer? Yes? Good. Let's continue. Okay, part B. At least 2 imperfections in 5 minutes. So T is 5. Lambda is alpha times T, which is 0.2 times 5. What is that? Yeah, that's 1. Okay. So P at least 2 is greater equal or less than equal. Greater equal to 2. What's greater equal? CDF is we want less than equal. So when we see greater than equal, we have to think about the complement. Complement is less than. Less than, we don't want less than, we want less than equal. So less than 2 is the same as less than equal to 1. Okay, and that is actually f of 1. Our lambda is 1 now, so you cannot like pick the value before, like 0.878. No, the number change because lambda change. Let's find our table. Okay, 1 is right here and 1, so that's 0.736. Okay, 0.736. 1 minus that. Okay. Yes, this is also a common mistake. Students forget the 1 minus that. Alright, so what do we get? So our answer is 0.264. Do you have the same answer? Good. So, and then next, at most 1 imperfections in 15 minutes. So the T is 15. Lambda is alpha times C, so 0.2 times 15 is, what is that? Well, that is 3, right? Okay, and at most 1 is what? Less than equal to 1. Whoa, that's exactly what we want. So that's 1, and the lambda is 3. Okay, let's come back to our table. Our lambda is 3. Okay, not here. So, next page. 3 right here. So, at 1, that is 0.199. So that's 0.199. And that's it for this problem. Do you have the same answers? Yay! Let's go to the next one. Okay, also pause here and try to work on the problems first before we continue. Okay, you ready? Let's go. Okay, so on average, see, average is really a keyword. When you hear the average, think about Poisson process. So alpha is 14.5 planes arrive per day. So the units is actually per day. Okay. Private airports. Find P number of arrivals on any one day between 12 and 15 inclusive. So T is 1 day. Okay, so lambda is alpha times T is 14.5 times 1 is 14.5. And we are looking for between 12 and 15 inclusive. Inclusive means include the endpoints. Exclusive means exclude the endpoints. So that is, let's draw a picture. I strongly recommend you to draw the picture every time because it's actually, it looks like easy, but many students make the mistakes. So please draw a picture. So you use less than equal to 15, subtract, do you want to subtract 12? No, we don't want to subtract the 12. We're going to subtract 11, so the 12 is left. Okay, so we have F. 15, my lambda is 14.5 minus 11, 14.5. Okay, so let's find it in our table. Let's go to our table. 14.5, not here. Let's go to the next page. 14.5. Yeah, here we see 14.5, but it's at most 9. We need 11 and 15, so not this page. We continue. Okay, so yeah, you actually need to look at the table and find the numbers, because I remember in the previous semester, there's some students in the exams asked me, oh, there's no value here. I cannot tell you why in the exam, because the answer is, because the values is in the next page, but I cannot tell you this in the exam. So it's many things that you have to work on it, and you know how it works, right? Yeah. On the exams, I can only answer like questions of the questions. Okay. All right. So lambda is 14.5 right here, and then 15 this number, and 11 this number. So 0.619 minus 0.220. 619 9 minus 0.220. So the answer is 0.399. Do you have the same answer? Good. Okay, let's continue. On average, average, right? Average, good. So that tells us alpha is 3 accidents per month in a large factory. Find 2 accidents next month. Next month is like 1 month, right? So T is also 1. Then lambda is alpha times T is also 3. Okay, then probability 2 accidents. Exactly 2. Well, that is exactly 2 is less than equal to 2. Subtract less than equal to 1. So that is capital F, 2. My lambda is 3. So you always write the first number is the K value, and then the second number is the parameter. Okay, don't mess up them. Okay, so and then we have 1. Oops, I put F1 and 3. Okay, let's find our table. Lambda is 3. So here we go back to the previous page. Okay, so we can see 3 was 3. Okay, lambda 3 is here. So 1 and 2. Right, so it's 0.423, subtract 0.199. 423, 0.199. Okay, what do we get here? So we get the answer is 0.224. Okay, so do you have the same answer? Good. So here I want to put a V mark. Okay, what color do you like? How about green? Okay, so V mark. So Poisson process is not only useful for time. So here today many examples like the T is 1 day, 2 minutes, 5 hours, etc. Okay, so actually Poisson process can work more than the time. It also works for other units. Okay, so like example 5 in your homework. Okay, you can work on like miles or milliliters, etc. Many other units. Okay. All right, so that is session 4.7. Remember, if you have questions, feel free to print screen and ask me through emails or visit our online office hours. Okay.